Okay, let's get started. In this short lecture, we deal with Banach spaces and we focus on section 2.11 of the textbook. What is a Banach space and why is it so important to begin with? It's not that complicated. In many cases, we seek a solution to an optimization problem with iterations. So we form a sequence of real numbers, vectors, sequences, yes, sequence of sequences, or a sequence of functions. And according to the idea, we want to find the solution to the optimization problem as the limit point of this sequence. How can we make this process work? So what do we need in order to make this process work? We want to know if we want to be sure if we can find a solution with iteration in a given vector space. So for instance, in the space of continuous functions, because we know that the solution must be a continuous function. We want to find a continuous function as a solution. We need to check two things. First, we need to check if the vector space is complete. This is a prerequisite. If it is complete, if the vector space is complete, then the limit point of any convergent sequence is in the same vector space. So there is no convergent. In other words, there is no convergent sequence in the vector space that has its limit outside the vector space. So once again, every convergent sequence converges to a limit in the same space, in the same normed vector space. If once again, if the sequence is a sequence, if the given sequence is a sequence of continuous functions, then the limit is also a continuous function. And second, we need to check if the given sequence we work with is convergent. If the answer is positive to both questions, then there is a solution for sure, and we can find it with iteration. So this is the reason why we need Banach spaces. We work with Banach spaces. We want to work with Banach spaces. It's not a big deal. We need a couple of definitions and a couple of examples. So first, we need the definition of Cauchy sequences. A sequence in a norm space, whatever it is, a norm space of vectors, a norm space of sequences, a norm space of functions. So a sequence in a norm space is said to be a Cauchy sequence if the difference between any two elements in the sequence at the far end approaches 0. In other words, we can reformulate this criterion to any positive epsilon. We can find an integer such that the difference between any two elements over this index, capital N, the difference, we can make the difference between any two elements of the sequence lying over this index, capital N, lower than epsilon. So we can, in other words, I'm trying to reformulate in many ways, we can make the difference between any two elements of the sequence arbitrarily small by increasing the indices of the elements. Okay, so at the far end, the point is at the far end, the difference between the elements of a sequence approaches 0. Most importantly, convergence is always measured with the norm of the vector space. So note that we work in normed vector spaces. A normed vector space has its own norm, and convergence is measured with this norm. Some important consequences. Every convergent sequence is in a norm space is a Cauchy sequence. So if we have a convergent sequence, then it is a Cauchy sequence. The reverse is not necessarily true. Note that. See the Stokey and Lucas textbook. They claim the same. So every convergent sequence is Cauchy sequence, but not every Cauchy sequence is a convergent sequence. So it's very useful because if we want to check if a sequence is convergent, then we only need to check if the sequence is a Cauchy sequence. How does it help? If we want to check if a sequence is convergent, we need its limit. But we can check if a sequence is a Cauchy sequence without knowing the limit. So to check if a sequence is a Cauchy sequence, we don't need the limit. We don't need to know the limit. But once we know that the sequence is a Cauchy sequence, we can be sure that the limit exists, even if we don't know it in advance. So the Cauchy criterion is very useful because by checking if a sequence meets this Cauchy criterion, then we can check if the sequence is convergent. And if the sequence is convergent, then its limit exists, even if we don't know it. Note that this limit is the point in the vector space we are looking for. So this is very useful. So in applications, we extensively use the Cauchy sequence, which can be formulated in many different but related ways. The difference between two elements of a Cauchy sequence tends towards 0 at the far end. Or in other words, we can reduce the difference between two elements arbitrarily to arbitrarily small values by increasing the indices of the elements. So we can find any positive epsilon, and we can reduce to any positive epsilon, we can find a capital N index, and elements over this index, the difference between elements with indices over this capital N will be smaller than epsilon. It's simpler to write the criterion than to spell it. Okay, complete normed space is the other definition for the day. A normed space, any normed space, is complete if and only if every Cauchy sequence in the space has its limit in the same space. So to be complete, a normed space must be such that any Cauchy sequence in the space has its limit in the same space. And a complete normed space is a Banach space. Okay, so theoretically, this is all to Banach spaces. So let's see two simple examples. Okay, let's have a look at these two examples. First of all, and most importantly, the real line is a Banach space. This is very useful because we can show the completeness of many other vector spaces with the completeness of the set of real numbers. And this is what we do in the next example. So the vector space, the norm space which we work with, is the space of continuous functions over the interval 0, 1 with the maximum norm. We have already known that this is a normed vector space. Now, which we are supposed to show that this vector space, norm space, is complete. Before proceeding, let's have a look at, just to be on the safe side, let's have a look at the norm of the vector space. This is the maximum norm, so the norm of any function, any continuous function from the space, is the maximum value of this function over the interval. So to show the completeness of this normed vector space, we need to show that any Cauchy sequence has a limit, has its limit in the same normed vector space. Suppose we have a Cauchy sequence. We can do this. So we have a Cauchy sequence in the normed space, and let's fix t from the relevant interval 0, 1. For any fixed t, we have the real numbers xnt and xmt, and the absolute value, this follows from the norm, the absolute value of their difference cannot be higher than the norm of the difference, because the norm finds the maximum difference. The norm finds that t where the difference of the functions is the highest. The sequence is a Cauchy sequence, so this difference, the norm, the norm of the difference approaches 0. So in sum, on this basis, it's easy to realize that we have a Cauchy sequence of real numbers for any t. And as the set of real numbers is complete, we have a real number xt for any t to which the sequence of functions converges. So in this case, we can show the completeness of the space of continuous functions with the completeness of the real numbers, because to any t, by the use of the Cauchy sequence of continuous functions, to any t, we have a Cauchy sequence of real numbers, and these real numbers converges to a limit point because the space of real numbers is complete. This is a very useful and interesting example, because at the same time we have encountered the concept of pointwise convergence. So to any t, the sequence of real numbers converges to x. So the sequence of functions pointwise converges to the function x.